Okay, for this video, I'll be going through combined science radioactivity tutorial MCQ. Okay, starting from number 1, in a simple model of an atom, X orbits around Y as shown. So X must be an electron, okay, and Y, it can either be a nucleus that contains protons that is positive and neutrons that is no charge, okay. So let us look at X. X must be a negatively charged electron because electrons are negative, and then Y will then be a positively charged nucleus. Okay, so answer is B. Question 2, a neutral atom consists of 17 electrons and 18 neutrons. So I have 17E, I have 18N. So what are its atomic number and nucleon number? So in your nuclide notation, okay, let's call this atom X. You have the nucleon number on top, okay, and atomic number at the bottom. Okay, nucleon number is actually the number of protons plus neutron. Atomic number is just the number of proton. But because they only give us electrons and because it is neutral, so I should have 17 protons. So I should have X17. And because I have 18 neutrons, so it will be 17 plus 18, so equals to 35. So I will get X35 and 17. So nucleon number is 35. Okay, and atomic number is 17. So answer is C. Okay, question 3. So again in nuclide notation, 133, 55X. So with this 55, I know there are 55 protons. Therefore, there will be 55 electron because it is a neutral atom. So I have 55 and 55. So then it boils down to the number of neutrons. So I have to look at 133. Okay, because this is the number that contains the number of protons and neutrons. And so 133 equals to 55 plus number of neutrons. So N equals to 78. Therefore, answer is your B. Okay, question 4. The reading on the detector placed near a radioactive material is 536 counts per second. Okay, the background count is 44 counts per second. So the half-life of the radioactive material is 34 hours. Now, what's the reading on the detector after 68 hours? So now on my detector, it is detecting 536 counts per second. Okay, and out of the 536, 44 is actually due to the background count. Okay, so actual sample is producing 492 counts, okay, per second. So after 34 hours, after one half-life, right? After one half-life, it will be 246 counts per second. Okay, this is for the sample. Okay, but because they want us to find the reading on the detector after 68 hours, and we always have this 44 background count, I will do one more half-life, okay, to get 34 hours. After one more, this is the second half-life. Okay, so 246 divided by 2 will be 123 counts per second. Okay, but because there are actually a background count of 44, that means the reading on the detector will now be 123 plus 44 background. So I'll get 167. So answer is D. Okay, question 5. Radioactive 14C was used to find the age of a wooden archaeological specimen. Measurements were taken in different situations. Hold on. Yep. Where the following count rates were obtained. So 1 gram sample of living wood is 105 counts per minute. 1 gram sample of archaeological specimen is 35 counts per minute. And with no sample is 25 counts per minute. That means this is the background count. Okay. So if the half-life of 14C is known to be 5,700 years, what was the approximate age of this archaeological specimen? So I now have 105. Let's bring in the background count. So this is the reading on the counter, 105. But because there's background count, so I need to take 105 minus 25 to get 80 counts per minute. This is due to the wood itself. Okay, after I subtract away the background count. For the 1 gram sample archaeological sample, I also need to get the background count deducted from here. So I get 10. Okay, so I get 10 counts per minute on the sample. Okay, on the sample. So now, how many half-life has it gone through? So I start off with 80. Okay, so after 1 half-life, I become 40. Okay, 1 half-life. Then after 1 more half-life, second half-life, it becomes 20. Then it should drop to 10 after third half-life. And 1 half-life is equal to 5,700. So 3 half-life will be 3 times 5700. So the answer will be D. Okay. So is there a easier way to do? So if you look at the solution here, this is the final half-life, right? So all this final count, okay, after n number of half-life. This is the number of counts at the initial, okay, after subtracting away the background count. Okay, so you know that half-life is every time you divide by 2. Therefore, you use this formula, half to the power of n, where n is the number of half-lives. Okay, so if you can use this formula, it will be good. If not, then you can use the brute force method, whereby you take initial of 80 divided by 40, divide by 2 to get 40, divide by 2 again to get 20, divide by 2 to get 10. So total you get 3 half-lives. Okay, so it's good to understand this method. That means times half to the power of n. Okay, question 6. When dealing with radioactive materials, there are possible dangers. So please read up on the dangers and how to protect yourself from the danger. Now, which statement is correct? So we have alpha, beta, and gamma. Okay, so we talk about the penetrating power and also the ionizing power. Okay, so alpha, if we talk about the penetrating power first, it is the highest. Okay, so alpha is the highest alpha is the lowest, because alpha is actually a helium nucleus, and you know that helium nucleus is large in size. Okay, so it is unable to pass through because of the size. Okay, and that will make gamma to be the highest penetrating power, because gamma is just like a kind of energy. Okay, like a gamma ray. Okay, then in terms of the ionizing power, okay, the highest will be your alpha. Okay, because it's actually a helium nucleus, so the charge is +2. So for beta, it is actually -1. Okay, so it's not as high of a ionizing power than alpha. And gamma, it is the lowest, okay, ionizing power, but it can penetrate very easily. Okay, so you need lead for its protection, a few cm of lead or concrete, right? For gamma, the ionizing power is low, but it can penetrate the most easily. Okay, so you need to memorize. Now, which statement is correct? Beta particles can pass through skin and damage body cells. Okay, this may be correct. Okay. For alpha, I can just block it with a piece of paper. Okay, a piece of paper. For beta, because it has a higher penetrating power, so it can pass through skin, and it can also damage body cells by ionization. Okay, now option B, let's look at option B. Materials that emit only alpha particles must be kept in thick lead containers. Don't have to be, because it can just be blocked by pieces of paper. So B is not correct. How about C? Radioactive materials are safe to handle after 2 half-life. That is not correct, right? Because after 2 half-life, the number of counts may still be very high. Okay, then D, sources of gamma radiations are dangerous because they have long half-life. Not necessarily. They are dangerous because of their penetrating power. Okay, they have the highest penetrating power. So you can read the answers here. D is wrong because sources of gamma radiations are dangerous because the extremely high energy of gamma ray allow them to penetrate just about anything. Okay, they have high penetrating power. Option C is wrong because some radioactive materials have a very short half-life and are dangerous to handle even after 2 half-lives. Okay, option B is wrong because alpha particles have the least penetrating power and can be absorbed by a few pieces of paper, so we do not need to keep them in thick lead containers. Okay, question 7 is this one. Which type of electromagnetic radiation is produced during radioactive decay? So the answer will be gamma rays, right? That is the gamma that we are talking about. Okay, so EM spectrum, I hope you still remember your radio, microwave, infrared, visible light, ultraviolet, X-ray, and gamma. So gamma is actually produced during radioactive decay. Okay. Okay, maybe I'll go on to do the structured question. Okay, so these are the answers. Which one of the particles in the atom is not charged? It will be your neutron. Okay, which particle in the atom has the smallest mass? It will be your electron. It is almost negligible mass when compared to neutron and proton. Which two particles in the atom have the same mass? Will be proton and neutron. What are the proton number and the nucleon number of a helium atom? They are asking for the atom. The number of proton is 2. Number of neutron is 2. So they are asking for the nucleon number, okay, and proton number. So it will be 4, 2. Okay, right? Because they are not just asking for the neutron number of neutrons, they are asking for the nucleon number, which is actually your mass number in chemistry. Now, state 2 differences between an alpha particle and a helium atom. Now, helium atom is actually neutral. Alpha particle is actually positive 2 in charge. Okay, so answer, an alpha particle is positively charged, right? There's no electrons, whereas a helium atom is electrically neutral. Now, an alpha particle has no electrons, it's just the nucleus, whereas a helium atom has actually 2 electrons. The mass of an alpha particle is slightly less than that of a helium atom because lack of the 2 little electrons. Okay, so this is question 1. Now, question 2. Okay, there are 2 stable naturally occurring isotopes of hydrogen. Okay, one is the common hydrogen, 1, okay, and has a proton number of 1 and nucleon number of 1. Hydrogen 2, deuterium, has a nucleon number of 2. There's also a radioactive isotope of hydrogen called tritium, hydrogen 3, with a nucleon number of 3. So what is isotope? Okay, isotopes are atoms of the same element with different number of neutrons but the same number of protons and electrons. So it is the difference lies in the number of neutrons, okay, for isotope. So please memorize the definition. Okay, basically they are atoms of the same element but with different number of neutrons but same number of protons and electrons. Okay, so let's look at part B. They want us to fill up the table with the number of protons, neutrons, and electrons of the neutral atoms. Okay, so for hydrogen is 1, 0, 1. Okay, for hydrogen 2 is number of neutrons is 1, 1, 1. This is 1, 2, 1. So hydrogen 3 is actually the heaviest, right? Because the total mass is 1 proton plus 2 neutron. Hydrogen 1 is actually the lightest, okay, because the total mass is actually 1. We don't count in the electrons, strictly speaking, because they don't really have mass. Okay, so suggest why isotopes have similar chemical properties. So they have similar chemical properties because they have the same number of protons and electrons. So it's not to be defined by the number of neutrons. Okay, so this one you actually learn in chemistry. Okay, if okay, we move on to the next question. Okay, the most abundant stable isotope of strontium is strontium 88. Okay, so what is isotope? Please remember the definition. Same element but different number of neutrons. Okay, same number of protons, same number of electrons. Now, a nuclide of strontium has a nuclear number of 88 and the proton number is 38. So, I do not know what is strontium's chemical formula. Okay, so if I just want to represent the number strontium, I will write the nuclear number 88 on top and the proton, oh sorry, I think it's SR, okay, given here. Okay, so there are students who ask me, hey, do I need to memorize the periodic table or do I need to have the periodic table? Actually, for physics, it's not really necessary for this chapter, but for chemistry, they'll provide. Okay, so I can see from here, strontium is actually represented by capital S, small letter R. So the nuclear number 88, proton number is 38, so I'll write 88 and 38 here. So I can actually know the number of protons to be 38, number of electrons if it is a neutral, okay, atom, then it will also be 38, and number of neutrons will be 88 minus 38 equals to 50. Okay, so explain what is meant by a nuclide of strontium. Okay, a nuclide of strontium refers to the strontium atom with a distinct number of protons and neutrons in the nucleus. Okay, so it's called the nuclide. So write down strontium 88 in nuclide notation. So I already did it. 88 extra 38. Okay, so number of neutrons I also have already calculated. 50. Number of electrons, because it is neutral, so it's also 38. So all this information, if you know chemistry, it is very easy. Okay, B part 1. Strontium 90 is a radioactive isotope produced by nuclear reactions. Okay, so that means I will have 90 strontium symbol. I still have the same number of proton. Okay, so that means my P equals to 38, my E is 38, but my N is actually 52. Okay, state how the composition of this isotope differs from that of strontium 88. I think I already answered this when I work this out. Number of neutrons is 52, number of protons is 38. Okay, but actually they're asking for the nuclide lah, so sometimes you don't need to bring in your electrons. Okay, because if it's neutral, then you can easily infer that the number of proton equals number of electron. Now, state one type of radiation that nuclear reactions could produce. So it can either be alpha, beta, and gamma. So they may give a following question to ask you about the ionizing power and the penetrating power. Okay, so again, you need to know what is your alpha, beta, and gamma radiation very well. Okay, so question 4, okay, is what we have been talking about. Okay, radiation, the nature, the charge, the penetrating ability, and the ionizing power. So this is a symbol for alpha. Okay, what are they asking for the nature? For this, I would think that it is a helium nucleus. Okay, the charge is positive 2, the ionizing power is high, okay, because of the high charge. Okay, so the penetrating ability is easily absorbed by a piece of paper, a tin, aluminium foil, or human skin. Okay, so that means it's not able to get into me unless I swallow it. Okay, for beta, the nature is actually an electron, a very high energy electron. The charge is negative. It can be, the penetrating ability is higher than alpha. Okay, I forgot what is the thing that it can penetrate. Later we will take a look. So the ionizing power is intermediate between alpha and gamma. So this is like the middle child. So if you know your alpha and gamma, beta will be the one in the middle. Okay, the nature of gamma is actually from your electromagnetic radiation. Okay, the charge is neutral, no charge. The penetrating ability is high. Okay, it can pass through, or rather, it can only be stopped by thick concrete or a few cm of lead. Okay, and the ionizing power is low because it doesn't have any charge. Okay, so let us take a look, compare my knowledge with the answer. Okay, so the nature, maybe you need to think, elaborate a little bit more. Just now I said it was only a helium nucleus. Instead, you should say consists of 2 protons and 2 neutrons tightly bound together. Okay, or you can say it's a helium nucleus, and that it consists of 2 protons and 2 neutrons tightly bound together. Okay, so that you make your answer more complete. So for beta, it's actually a fast moving electron ejected from a radioactive nucleus. Okay, something like what I say, it has energy. This electron is ejected with a lot of energy. Okay, then EM spectrum, so positive, negative, neutral, or no charge. I got that. So for beta, it is absorbed by a piece of aluminium that is a few mm thick. Okay, a few mm thick. And for gamma, it passes through most materials easily, absorbed by lead that is a few cm thick or very thick concrete. Okay, so you need to know this because they always like to ask the ionizing power and the penetrating ability. Okay, so B, very small quantities of radioactive isotope are used to check blood circulation by injecting it into the bloodstream. Now this kind of questions is very tricky, or is common, and they like to ask you for which type is used. Okay, suggest 2 criteria for such a radioactive isotope to be injected into the bloodstream. So I would really memorize this. What are the 2 criteria? So the first one is the half-life must be short. What is the purpose? Because if the half-life is short, it will not stay in my body. It will undergo decay, and after it has served its purpose, right, I don't want it in my body anymore. Okay, and the other one, it must be the isotope must not be poisonous to the body. Okay, so B part 2, what are they asking? Okay, B part 2, they want us to describe how to check that the blood circulation is good using this radioactive isotope. Okay, so this is an application question. We use a detector, so it's the GM counter, a Geiger-Müller detector counter, to pick up radiation from the radioactive isotope at different points of the body. If a high count rate is detected, it indicates that the blood circulation is good. Okay, if the blood circulation is poor, then if I inject into this part of the body, okay, it doesn't travel down to the other part of the body. So maybe this is my arms and this is my toes. So at my toes, I don't see that there's a high count rate. It means that the blood circulation may not be so good. Okay, part 3, explain why gamma emitting isotope is used to check blood circulation rather than another isotope that emits alpha or beta. So this one boils down to the application of your radioactive isotopes. Okay, so why do we choose one that emits gamma rather than alpha or beta? Okay, now alpha particles are absorbed by the tissues and human skin, so the radiation will not be detected. Okay, beta particles may be largely absorbed and it's not penetrative enough still. Okay, so the radiation will not be detected, but gamma rays are very penetrative and can penetrate the tissues and leave the body to reach the detector. Because this thing was injected in the body, it's the same question stem, right? So my detector is actually placed outside the body. So if it's alpha or beta, they might be, or they will be absorbed by the body tissues. They may not be able to pass through the body tissues and the skin to reach the detector that is outside of the body. However, gamma is very penetrative. Okay, but of course I don't inject a large amount lah. Okay, then question 5. Okay, ignore this part. Okay, the next question. This graph shows how the count rate in a sample of radioactive isotope plutonium-238 changes with time. Okay, so this is the graph that is being provided. State what is meant by half-life in radioactivity. So you need to memorize this. The half-life is the interval of time required for half of the nuclei of a radioactive sample to decay. So this is a definition that you need to memorize. Okay. Part 2, use the graph to find the half-life of plutonium-238, showing clearly on the graph how you obtain your answer. So we started off with 1000. Okay. So after 1000, half of it will be 500. The counts will drop to 500. So we have to look at this carefully. Okay, and so it is about 85 years. Okay, so do we actually need to take into account the background count? So in this question, they didn't tell us about the background count. They just tell us the count rate. Okay, so unless in the end the graph tapers off to a flat level, okay, then you may need to bring in background count. Okay, state one important assumption for your answer. The background count has been corrected in the graph given. Okay, so this is the assumption. But I think for O level, they may be very specific or very explicit to tell you whether to bring in background count or not. Okay, then look at part B. The Cassini spacecraft launched in 1997 took 7 years to reach Saturn. The electricity to power is generated using the energy produced from the decay. It decays by emitting alpha. This is important. During the 13 years that Cassini orbited Saturn, output from the generators will decrease. Explain why. Okay, so it's in 1997. Okay, the half-life is 85. So because as the time goes by, fewer plutonium nuclei are left to decay over time. So half-life means the sample, the count rate goes to half. In between, the number will drop. It's just that half-life tells us the time taken for half of it to decay. Okay, so throughout this 13 years, there's always a radioactive decay to provide the energy to the spacecraft. Okay, so as the decay continues, we will have lesser nuclei and therefore the power will get run down. Okay, now discuss the hazard of launching a plutonium-238 power satellite into space. Okay, so any explosion of the satellite during the launch will release radioactive materials into the atmosphere. Okay, and because the half-life is 85 years and the alpha radiation spreading around will take a long time to disappear, that means there will always be this radioactive substance. Okay, after 85 years, then half the sample will then be gone. Okay, leaving behind another half. Then our next generation will have to bear with this half for another half-life, and it will drop from 1000 to 500 to 250, so on and so forth. Okay. Okay, part D, plutonium-238 is highly dangerous. A tiny amount is enough to kill a human. Explain why it's unlikely to cause any harm if it's outside the body, but it's likely to kill if it's inside the body. If it's outside the body, remember, it actually emits alpha particle. so it can actually be blocked by our skin. Okay, so when it's emitted outside the body, they cannot penetrate the body due to their low penetrative power. But when it's taken inside the body, alpha particles produced are easily absorbed by cells, so it has high ionization power, so it will cause mutations or it can kill cells or tissues. Okay, so the human may develop cancerous cells. Okay, so this is question 5. Now question 6, it is this one. Some isotopes undergo nuclear decay. Explain what is meant by nuclear decay. Okay, so nuclear decay is a random and spontaneous process. Random because we cannot predict when it will happen. Okay, and spontaneous is because we cannot cause it to happen. It just happens by itself. Okay, so this is the process whereby an unstable nucleus loses energy by emitting radiation or particle. So we have this carbon 12C6. We also have another carbon, which is another isotope of carbon, is 14C6. So this is the one that is radioactive because the nucleus is unstable. Okay, so it is just a natural, random and spontaneous process, but for carbon it will just remain very stable. Okay, so this is what you need to memorize for when they ask you for explain what is nuclear decay. Now state 3 types of radiation that may be emitted. So it's your alpha, beta and gamma radiation. Okay, so with this they can actually follow up with the penetrating power and ionization power. Okay, now state 2 common practical uses of radioactive nuclides. So any 2, so you can actually get this from your notes. Okay, need to spend some time to memorize. State 1 hazard. Okay, development of cancer cells, damage to living tissues, cells and DNA. Don't straight away say it will kill human. Okay, so go by this. The cancer cells will eventually cause a human to die, right? It can damage living tissues, but the human may not die. Okay, and it may cause a defect, birth defect. Okay, so please do not just say the human will die. Okay, then the next one, technician sets up a radiation detector in a lab. So before is brought in, the detector register a low count rate. So this is actually the background count. So state the name of a suitable detector. It is actually the Geiger-Müller counter. Okay, you need to know this. Suggest what causes the low count rate before any radioactive source is placed near the detector. 1 mark. So this is actually your background radiation. Okay, so this can be radiations from building materials, radon gas, cosmic ray, and even in some food such as bananas and carrots. Okay, but they are quite low. Okay, so it's pretty safe, right? It won't kill us, it won't cause us to develop cancerous cells. Okay, so this is just in the background. Okay, part C, a radioactive source that emits alpha is placed on the lab bench and the source is gradually moved closer. So at first continues to register a low count rate in the background, but as it gets nearer and nearer, okay, the count rate suddenly increases to a very high value. Okay, explain these changes in the count rate. So we need to, I think the answer is due to it being an alpha. Okay, because the alpha penetrating power is very low, right? Okay, the detector registers a slightly less low count rate than the background due to the random nature of radioactivity. So the background count rate, you can say that is maybe like 44 counts per minute, but this is just the average value. Sometimes you will drop lesser than that. Okay, the very high reading is due to alpha particles emitted from the radioactive source, and because it's now placed close to the detector, remember the detector was slowly moved closer, okay, as alpha particles have a short range of penetration, right? Okay, technician sets up the same equipment with the same source every year in the same way. He noticed that the count rate registered by the detector every year is slightly smaller, right? Suggest why this is so. Because half-life, the rate of decay of the source decreases every year, right? The number of nucleus that are left after the decay, every month, every year gets lesser and lesser. Okay, and the half-life of the source is much longer than a year, or there are fewer radioactive nuclei left for decay every year. Okay, and the half-life of the source is much longer than a year. Okay, so suggest a way to store this safely. You can be put in a box made of lead. Okay, so of course I know alpha particle, it is can be blocked by few pieces of paper. It may not be able to pass through the human skin into the body, but because they are still radioactive, so why not I just put it in a box made of lead. Okay, so because lead, it can also block my gamma radiation. Okay, let's look at the next question. Now, in a nuclear power station, radiation detector is connected to a computer. Readings recorded are displayed on the computer screen. Detector is switched on. 10 minutes later, at time t equals to 10, a small sample of radioactive material is removed from a nuclear reactor and placed near to the detector. So readings are recorded for a further 40 minutes. So the graph shows the display on the computer screen. So this is actually initial 10 minutes. So we can actually see that the background count is actually 12 per minute. Okay, background count. Then when I introduce the sample, it jumped up to 84 counts per minute. Okay, which means to say, part A, determine the background count. So suggest one source of this background count we covered already: radiation from rocks, ground, building materials, radon gas, radiation from space, cosmic ray, or nuclear waste. Okay, so you need to memorize this. They like to ask. Now use the graph to determine the count rate due to the radioactive sample at the following time at t equals to 10. So just now I read out from the graph is 84 counts per minute, but don't forget we actually have a background count of 12. So the actual is actually 84 minus 12 equals to 72 counts, and this 72 counts per minute is then due to the radioactive source. Okay, so just now we did one question whereby we don't know whether is there any background count or not, right? So this question 10 is very clear. It shows you that there's actually a background count. In fact, they will actually ask you what is the amount of background count. Okay, so the background count is actually 12. So 84 minus 12, we get 72 counts per minute. Okay, so see part 2. At t equals to 19 minutes. Okay, so at t equals to 19 minutes, I read off is about 21. Okay, 21. So what is the count? Is actually 9 counts per minute. So again, we take into account that there is a background count. So it becomes 9 counts per minute. Okay, so with that, they want us to calculate the half-life. Okay, so you see 72, after one half-life it becomes 36, 36 becomes 18, 18 becomes 9. Okay, so that is why we have C part 2 to be 9 counts. At first it looks like a strange number, but if we work this out, then we know, oh, why is it 9? Okay, because every half-life the number of nucleus left to decay will be half. Okay, so this is actually 1 half-life, 2 half-life, and 3 half-life. Okay, so this initially it was 72 at 10 minutes. After 9 minutes, okay, after 3 half-life, it dropped to number of the counts to be 9 per minute. That means the half-life is 3 minutes. Okay, so please make sure you understand this. Now, how about we use this formula? This is the final number, okay, the number of counts, and this is the initial. So we multiply by half to the power of n, where n is the number of half-life that it has gone through for this number, initial number, to drop to 9. So if you do your math, 9 equals to 72 times half, and okay, I know some of you may be put off by this. No, so this becomes 9 over 72 equals to half to the power of n. Then you will get a divide by 3, divide by 9, so 8, 1 over 8. Okay, so you have to do some math calculation for this. If not, you can always check using this. I think it's easier for you to divide by 2, divide by 2. Okay, hopefully they don't go to too many half-life. Okay, then part is explain why the count rate remains constant after 30 minutes. So after 30 minutes, do you see that after going through 3 half-life, the number actually dropped to 9. So if I were to let it go to one more half-life, the fourth one, it will drop to 4.5. Then if I let it continue, it will drop to 2.25. Okay, and each half-life is actually 3 minutes. So even after 5 half-life of 15 minutes, right, the number already dropped to 2.25 counts from the sample, and this is very, very little compared to the background count of 12. So it becomes sort of negligible, right? So after 30 minutes, and that is actually 10 half-life, you know. Okay, so the radioactive sample has already completely decayed. Okay, so that's why it dropped to the background count of 12. Now, suggest two disadvantages of using nuclear power. You know, Singapore may be exploring the idea of developing nuclear power plant. Okay, so this one you need to memorize. The creation of radioactive waste is dangerous to human health. Okay, there may be some nucleus that is included in this nuclear radioactive waste that is passed out from the nuclear plant. Okay, so this may be dangerous to human health. Then safe disposal of radioactive waste is difficult and expensive. So imagine they decided to use one radioactive element that has a very long half-life, so it may remain with us for many, many years. Okay, any more question? Okay, so I think that's about it.